Modern PV manufacturing processes produce cells with a relatively large variance in their power output capability. Panel manufacturers seek to reduce this variance by assembling panels from pre-sorted cells. Nevertheless, panel models on the market today still have a plus or minus 3% variance in output power. Moreover, each panel has a slightly different MPP current. When several panels are connected in series, traditional centralized inverters cannot draw the optimal current from each panel. Instead, the inverter selects the current that gives the average peak power point of the string or the array. This peak power is always less than the theoretical sum of the individual peak power points of every panel. The power loss resulting from this panel mismatch amounts to 3 to 5% on average. The power loss from partial shading occurs when part of a panel is shaded, causing different levels of illumination on the cells in the panel. When a panel is partially shaded, its voltage may reverse. This can result in panel damage due to overheating. All PV systems prevent this in one of two ways. The panel bypass diodes conduct, causing shaded panels to lose from 1/3 to all of their power. Alternatively, the inverter readjusts the current flowing in the whole string to a lower value acceptable by the shaded panels. In either case, power loss in partially shaded arrays is significantly greater than the reduction in the illuminated area, because power output is lost also by non-shaded cells and panels. In typical residential roofs, shading cannot be completely avoided. On average, partial shading losses amount to between 5 and 25%. Inverters will only function between a predefined minimum and maximum voltage. If the solar array produces too little voltage, for example, due to high temperatures and short strings, the inverter will reduce the string current below the optimal operating point until this situation is resolved, resulting in power loss. Undervoltage is unavoidable in many cases where short strings are required. A survey estimated that over a quarter of PV installations in California experienced power losses of at least 15% due to undervoltage. The efficiency of the inverter maximum power point tracking depends on its algorithm's ability to identify the array's peak power point at any given time. Changing environmental conditions can have a significant impact on how effectively traditional inverters can identify this peak. For example, shading can cause the array's power curve to exhibit more than one maximum power point, and many MPP tracking algorithms are not designed to handle these local peaks efficiently. When the MPPT is mistakenly locked on a local peak, the MPPT efficiency falls dramatically, creating static power losses. Dynamic losses are directly related to the speed and accuracy of the MPP tracking algorithm. The peak power point can move quickly due to frequent changes in irradiance level on windy, cloudy days. Traditional inverters will struggle to keep tracking MPP with these changing conditions. Power losses due to suboptimal MPP tracking typically vary from between 3 and 10%. To summarize, traditional PV systems suffer from various inherent power losses, stemming from a centralized topology. SolarEdge increases energy output by up to 25% while reducing system cost and simplifying design and installation. The SolarEdge system is comprised of 3 key elements. SolarEdge Power Box, which is integrated on each solar module in place of the junction box. A simplified, highly reliable inverter, and an integrated panel-level monitoring system. The SolarEdge Power Box optimizes power harvesting by performing MPP tracking for each panel individually while keeping the string voltage fixed. Here we see the IV curves of 2 solar panels fitted with SolarEdge power boxes. You can see that the MPP point is different for each panel. As you recall, traditional systems cannot handle this mismatch and will adjust to an average point, resulting in power losses. In contrast, the SolarEdge system easily manages MPP tracking individually for each panel, harvesting the optimal available power. This same capability also ensures the SolarEdge system will harvest more power in partial shading situations. The shaded panel produces as much as it can, while other panels in the string are not affected and continue to produce at their maximum peak point. In traditional systems, high temperature or shorter strings may lead to power losses due to string undervoltage. SolarEdge prevents it by maintaining string voltage fixed at the optimal DC to AC conversion point, while independently controlling the panel voltage. Last, panel-level MPP tracking can better identify the global peak of the power curve. It also allows for noticeably faster tracking compared to centralized inverters, especially during dynamic weather conditions. To summarize, SolarEdge distributed DC architecture can increase energy production by up to 25%.